If you open up Microsoft Word, on your keyboard, hold Alt and then the equals sign. Hit Alt equals. It pulls up something that says type equation here, and it's what you do to make your math look nice. Like if you want e to the x to look really nice, or square root, you type in that \sqrt, and now you can do pretty looking math equations. Well, anyways, I bring it up because you guys are talking about there's pi, and then there's capital pi with a capital P. If you do the backslash and then capital PI, that's the capital pi. What you guys see right on your homework is probably a product symbol, I assume. So if you type in \prod for product, you get a super jumbo pi. And this is, you're right, this is like saying, hold on, I gotta do it again so I can give it a, this is like saying 1 squared times 2 squared times 3 squared. Right? Instead of a sum, like the capital sigma notation, it tells you to take a product. Like that. Okay. Now, let's talk about what we got going on today. We've got counting principles. And some of this stuff maybe is a review from earlier this semester, but 2 or more sets are disjoint if they share no elements in common. If I want a union of many sets, we may sometimes choose to use the following notation. Again, just like the sum and just like the product, if I want the union of a whole bunch of sets, like set A1 union with set A2, union with set A3, and so on, I could use a really big union symbol, just like the really big sigma or the really big pi symbol, and then define an index variable with a start point and an end point for my index, and then, you know, maybe if this was a k equals 1 through 3, I'd have the union of A1, A2, and A3. Okay, so I bring that up because of the rule of sum. It says if a set A is a union of n disjoint sets, where I use a little subscript to say which set I'm talking about, well then the cardinality of A, which is like the number of elements in the set A, is the sum of the cardinalities of those disjoint subsets that we unioned together. And because they're disjoint, they don't share any elements in common. And so to count the total number of elements in my union of sets, I add up each of the cardinalities. This is the rule of counting in 2 ways. It says when 2 formulas enumerate the same set, and enumerate's a fancy word for count, when 2 formulas are counting the same set, then they must be equal. Here's an example. If I were to show you a grid like this, I've got 5 dots, 1, 2, 3, 4, 5, let's say. Oops. And 5 dots. So I'm trying to make a full grid of dots, and it's going to take me a few seconds. I didn't think it would take this long to draw 25 dots. I should have pre-drawn these ahead of time. Okay, so I have in total how many dots? N plus 1 squared. Do you see I have n plus 1 squared dots in my grid? But another way I could count these is I could count by diagonals. All right, so here's 1, here's 2, here's 3, here's 4. And what I've laid out here in these 4 diagonals is something like the sum of k, where k goes from 1 to n. Right? Because this is k equals 1, this is k equals 2, this is k equals 3, and this is k equals 4. And that's not quite the entire square, is it? It's about half of the square, because there's another half down here. So let's multiply that by 2. And then I could add to it this part. How many dots are on that main diagonal? That would be n plus 1. So this is counting in 2 ways. The first one, just the formula for a square, is n plus 1 squared to get the total number of dots. And then this is the second way of counting by the diagonals here in orange. And the principle of counting in 2 ways says that since this formula is counting the same thing as this formula, they have to be equal to each other. And so I could subtract an n minus 1 from both sides. And if I subtract n minus 1 from both sides, it's not going to be n plus 1 times n plus 1, but it would just be n times n plus 1, because I took away one of those copies of n plus 1. And then I divide both sides by 2. And I get this formula. Have we already done this in this class? Have you seen the triangular numbers yet? No? Okay, so here's a puzzle. What is the sum of 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 and so on plus 98 plus 99 plus 100? What do I get if I add up all the numbers between 1 and 100?
Is it 5,050?
It's 5,050. How did you get 5,050?
I said n is equal to 100, and I did 100 times 101, and divide that by 2.
Yep. So this sum right here is saying I'm going to have an index variable k, and it starts at 1 and it goes up to n. And every single term that I'm adding together just looks like k. So first it's 1, and then it's plus 2, and then it's plus 3, and then it's plus 4, and it counts up larger and larger numbers until I get to n. Well, that's exactly what this looks like if n is 100. 1 plus 2 plus 3 plus 4, and so on. So to quickly add up 1 plus 2 plus 3 plus 4 all the way up to 100, I could just take 100 times 101 divided by 2. So that's like 10,100 divided by 2, which is 5,050. Yeah. So these are called the triangular numbers. And that means the number 5,050 is the 100th triangular number. But the main thing that I like about this is it's a relatively easy way to demonstrate the rule of counting in two ways. First, we counted these dots in blue by calling them n plus 1 squared, and then we counted them a second way by diagonals. We set those equal to each other because these two formulas, blue and orange, are counting the same thing. They must be equal to each other, and that's how we can come up with a cool theorem like that. On the first day of class, I think, maybe the second day of class, we talked about the Cartesian product. And the Cartesian product of two sets is the set of all ordered pairs, where the first element in the ordered pair comes from one set, we'll call it A, and then the second element in the ordered pair comes from set B. We also talked in the same lecture, I think, about cardinal multiplication, which is to say if you want the cardinality of the Cartesian product of two sets, it's just the product of their cardinalities. And we did an example that was maybe something like this. If I want the Cartesian product of this set A and B, where A is the set 1, 2, 3, and B is the set 4, 5, we are talking about 1, 4, 1, 5, 2, 4, 2, 5, and 3, 4, 3, 5. That is the set that results from the Cartesian product of A and B. And so if I want the cardinality of this Cartesian product, that's the same thing as the cardinality of A times the cardinality of B, which is 3 times 2, which is 6. In other words, there's 6 elements in my set, right? Okay, so we might occasionally come across some word problems like this one. Suppose you attend your friend's wedding, and at the reception, you get to select your dinner. There's 2 choices of appetizer, 3 choices of entree, and 3 choices of dessert. You need to select one of each. How many unique meals can be created from these choices? I don't think it's 24. Yeah, it's 18. Because I've got, here we go, 2 choices of appetizer, 3 choices of entree, and 3 choices of dessert.
I was looking at the RSVP.
Oh, sorry, that was misleading. Yeah, sorry, the visual is unrelated. This is 18. And the reason we're doing multiplication here is because these are separate sets. I have a separate set for appetizer choices, entree choices, and dessert choices. And what I'm actually doing here is creating a Cartesian product. Where if like my set of appetizers that you're allowed to have is like, I don't know, what are appetizers that you get served at a wedding? Bread and caviar. I don't know. These are gonna be dumb examples because I'm thinking on my feet. But like, if I've got 2 appetizers and 3 entrees, steak, fish, and beans. Well, then like, what's the what's the Cartesian product between appetizers and entrees? It would be one ordered pair where you have bread and then steak. You have another ordered pair where you have bread and fish. You have another ordered pair where you have bread and beans. You've got bread and beans. Yeah, it's very British. Good, solid British wedding. Caviar. Caviar. I don't know how to spell that. Whatever. This is math. This is math class. And if I take a Cartesian product, I'm taking ordered pairs, right? And by the time I take the Cartesian product between appetizers and entrees and desserts, now I've got ordered triples, right? Ordered triplets. But I just have to multiply by the cardinality of all three of those sets to get the final cardinality. So I do 2 times 3 times 3, and that gives me 18. And that's the idea. New question. Suppose you're a traveling salesman and you need to drive to 5 different cities this week to meet clients. You're responsible for making your own schedule, so you can put those 5 cities in any order you like. How many different ways can you put 5 cities in order? What is 5 factorial, Hudson?
5 times 4 times 3 times 2.
Yes, because I've got a list with 5 blanks on it. And I've got 5 choices for the way that I can possibly choose my first city, right? And then how many choices do I have for choosing my second city? Just 4. And how many choices do I have for choosing my third city? Yeah, 2 of them are already taken, so there's only 3 choices. And then how many choices do I have for choosing the last city that I visit?
I mean, you could choose to not visit it. 1.
No, you need to. You have to.
You
So
need to.
using the same kind of logic here, I multiply through by the number of independent choices I have at each stage here, and we get 5 factorial. 5 times 4 times 3 times 2 times 1, which is like 120. So this question type is called a permutation. A permutation of a set is an arrangement of its elements in order. Like if I've got 5 cities and I ask you how many different ways can I arrange 5 cities in order, you're asking how many different permutations of this set exist. And the factorial is how you calculate the number of permutations. That's probably the wrong exercise number, but it's probably exercise 3 now. I need to fix that. Okay. Next, you're judging a chili cook-off and there's 10 competitors. You have to rank all 10 chilies on your scorecard, 1 through 10. So that way you can do a ranked choice voting algorithm, right? How many different ways can you put 10 different chilies in order?
10 factorial.
10! Right?
Sorry.
10 factorial, right? 10 times 9 times 8 times 6 times 6 and so on.
That's a lot. That's too many.
Okay, new question. Your toddler is playing with blocks. There are 5 unique blocks. There's a red block, a blue,
A red block.
Yep.
And a red block.
a blue block and a green block, and an orange block and a purple block. Your toddler has tiny hands that can only hold 2 blocks at a time. 1 block per hand. How many different ways can your toddler choose 2 out of the 5 blocks to hold?
Does it matter which hand he holds which one in?
No.
10.
10?
Yeah.
I think.
10.
Just come up with 10. Yeah, so this is a pretty easy one to think about, right? This is 1 combination, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? 10. And every time I teach statistics, we do this problem together, And a student always raises their hand and asks me, is that because 2 times 5 equals 10? The answer is not really. That's just a coincidence, right? Like, it's not always the number of blocks you're choosing times the total number of blocks. That just happens to be a coincidence. It's not really the underlying reason why the answer is 10 here. To make this a little bit more difficult for you guys, you go to compete in a golf tournament where there are 12 total golfers. They divide the golfers into groups of 4 that go through the course together. The first group of 4 that gets to play the course starting from hole 1 is selected at random. How many different ways can they choose 4 out of the 12 golfers to be in group 1? And imagine that all 12 of these golfers are distinct. There's no identical twins. We can tell them apart. So how many different ways can I create a group of 4?
Why is he so jumping? Golf is not that exciting.
Yeah, bro, seriously.
That is, yeah. That is a strong display of empathy for the guy who made the putt. Okay. So the logic here goes like this. We are going to rank or permute the 12 golfers. And how many different ways can I rank 12 golfers, right? I don't mean by skill level or by age or anything. I just mean like in general. Like how many different ways can I put 12 golfers in order?
12 factorial.
Yeah, so I end up with 12 factorial permutations of this set. Step number 2. We're going to draw a line separating number 4 and number 5. Okay, so imagine this. I've got 12 golfers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Each dot gets to be a golfer. And here, there's a line separating these 4 that get to be part of my group and the other 8 that don't get to be part of my group. Now, I don't care about the order of the first 4 golfers. What does that mean? I don't care whether or not this dot is Bob and this dot is Jim, or this dot is Jim and this dot is Bob, right? How many different copies of this exact situation where I have the same first 4 golfers and the same last 8 golfers exist, where everything is exactly the same, these guys are all in the same order, but these first 4 happen to be in different orders, all shuffled around? 4 factorial. There's 4 factorial different instances within these 12 factorial permutations where these back half, the last 8 golfers are the same, but the first 4 are the same and then moved around. And since I don't care what order they're in, I should take my 12 factorial permutations and divide by 4 factorial. And that way, I can get rid of all of those extra permutations that are essentially the same for me. The next thing too, in step number 4 here, would say, I don't care about the order, their order. I don't care about the order of the last 8 golfers. And so if I've got the same permutations, let's say the first 4 are the same, but the last 8 can mix around and be in any order they want. I don't care about how that happens either. How many copies of what are essentially the same permutations do I get where the last 8 are shuffled around? 8 factorial. So to get the correct count, I start off with 12 factorial. That's how many different ways I can order these 12 golfers. I divide by 4 factorial because I don't care about the order of the first 4. I divide by 8 factorial because I don't care about the order of the last 8 either. And dividing by those numbers will eliminate the redundant duplicate copies of this grouping. So that's how many ways we have to choose a group of 4 golfers. And so 12 factorial is the same thing as 12 times 11 times 10 times 9 times 8 factorial. 4 factorial is 4 times 3 times 2. So notice the 8 factorials cancel. And then you get like 12 divided by 4 is 3 times 11. 10 divided by 2 is 5, and 9 divided by 3 is 3. So you get like, what is that? 11 times 45, which is that.
That's what Carter got, so I think it's right.
Nice. Good. So vocabulary words, right? Whenever I do this, whenever I have a set and I select a subset of its elements, we call this a combination. Choosing 2 out of 5 blocks was a combination of the blocks, and choosing 4 out of 12 golfers is a combination of the golfers. The binomial coefficient is a function of 2 positive integers that will tell us the number of combinations. So whenever I have a binomial coefficient, I write the total number on top and the smaller number on the bottom. The number of elements I want in my subset goes on the bottom. That's k. So in the last example, we had 12 golfers. Choose 4 of the golfers, and that was 12 factorial divided by 4 factorial divided by 12 minus 4, which was 8 factorial. And when you read this out loud, you see this on paper, you call it n choose k. So 12 choose 4 is 495. So far, so good? Okay. Really quick, lightning round. You're eating at Genghis Grill and there's 8 types of protein. Only 3 can go into your bowl. How many ways can you choose 3 out of 8? That's 8 choose 3. 8 factorial divided by 3 factorial and divided by what? 8 minus 3 is 5 factorial. So that's 8 times 7 times 6 divided by 3 times 2. That's 4 times 7 times 2. 56. Cool. While visiting your nephew, he asks you, what are your top 3 favorite Power Rangers in order? So if there's 7 Power Rangers, I've got to choose 3 of those Power Rangers to be in my top 3. And according to my nephew, I have to put those 3 in order. So the first act is a combination. It's 7 choose 3. But then I also have to place them in order. And there's multiple ways I can put 3 of them in order, right? There's actually 3 factorial ways I can place these in order. And so it would be 7 factorial divided by 3 factorial divided by 7 minus 3 factorial times 3 factorial. What's my answer here? This is called a partial permutation. because I'm only permuting part of the set. And I calculate this by first doing the combination problem, 7 choose 3, and then multiplying by the number of ways I can permute 3. Partial permutation. You also notice that like whenever I took n factorial divided by k factorial divided by n minus k factorial times k factorial, the k factorial is canceled. And so the formula for partial permutation simplifies to just that. That's my partial permutation. Let's skip ahead. You own 3 identical white t-shirts. Two identical red t-shirts. And 2 identical blue t-shirts. How many different ways can you wear all of these t-shirts during the course of 7 days? And in this question, you only get exactly 1 t-shirt per day. You can't skip wearing a t-shirt, and you can't wear 2 on the same day. So, what do you think? This thinking through the problem is going to work a lot like with our golfers. I'm going to make a row of 7 dots where each dot gets to represent a t-shirt. And pretend for a moment that these are all distinct t-shirts, right? What if I could tell these apart? How many different ways can I permute 7 t-shirts? 7 factorial permutations. But then I'm going to have groups of 3, 2, and 2. Maybe I misspoke. Maybe the better way to think about this is each one of those dots is a day of the week. Right? Imagine each dot as being either Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And as I permute these and then place these little partitions, these 3 days of the week get to be white t-shirt days. And these 2 days of the week get to be red t-shirt days. And then the last 2 days, whatever they might be, Tuesday and Friday, are going to be blue t-shirt days. Now, if I can't tell the difference between my white shirts and I can't tell the difference between the blue shirts, then I don't care about the order of these guys. I don't care about this order. And I don't care about this order either. And I don't care about this order either. And when I don't care about how I can place things in order, how do I get rid of all those extra copies of those permutations? We're going to divide by 3 factorial to get rid of the extra copies where I, have exactly the same permutation except for the first 3. And then we're going to divide by 2 factorial so I can have exactly, the same permutation except for these first 2 switched around. And then divide by another 2 factorial in case I have the whole permutation exactly the same but the last 2 switched around. And that's how we do it. So again, this would be 7 times 6 times 5 times 4, and the 3 factorial cancels, divided by 2 times 2, and 7 times 6 times 5, it's 210 again. What a coincidence. But you see what's happening. This is called partitioning a set, where I take a set like the number of days in a week and then I partition them into different buckets, right? In this case, there's a white shirt bucket and a red shirt bucket and a blue shirt bucket, and count them up. This is called partitioning. There's the word. Sorting of its elements into multiple subsets. And the way we calculate this is with a multinomial coefficient. And unlike the binomial coefficient, it really doesn't even save you any time to, I mean, I guess you don't have to write little factorials, right? I mean, sometimes you see this occasionally in papers and stuff, but you could also just write this down. It's the total number factorial divided by the size factorial of every subset you're sorting into. Questions about that? No? This says that you're designing a stylish tile border in your bathroom. On hand, what do you have? 4 identical brown tiles, 5 identical blue tiles, and 6 identical green tiles. And I cannot tell the difference between blue tiles. I can't tell the difference between green tiles. And so what I need to do is get the total number of tiles, which is 15, and say I'm going to sort these 15 tiles into buckets, right? Are they going to be brown, blue, or green? And this is a partitioning of the set. And so that's how you count them up. Get a feel for it. All right. You open a new deck of playing cards and randomly shuffle the deck over and over again until they're shuffled really, really well. What's the probability that the cards are now in exactly the same order in which they came? You said 52 factorial?
I said 52 factorial.
We went over that.
Yeah, there you go. So there's one
Oh, yeah, because that would be a big percentage.
order in which they came. There's one order in which they came out of how many possible orders? Well, 52 factorial orders. And 52 factorial is a really, really, really big number. You probably don't fully appreciate how large 52 factorial is. At one point, someone who understands physics a little bit better than me had told me that 52 factorial is a number larger than the number of atoms in the observable universe. So it's a big number. And so it's highly unlikely that you're going to ever shuffle a deck randomly back into order. In fact, another funny way of thinking about this is like if you shuffle a deck of playing cards, the exact order those cards are in is probably the first time a deck of playing cards has ever been in that order, like in the history of the world, right? Every time you shuffle a deck, you're creating an order of playing cards that's never been created before. All right, find the prime factorization of the number 3,960. I did not do prime factorizations except in like 6th grade or something, you know, like it's not a topic that comes up a lot in school, but you probably remember doing this once from grade school. Here's how you do prime factorizations. You ask yourself, is this number divisible by 2?
Yes.
Okay. What is 3,960 divided by 2?
1982.
Okay, is that number divisible by 2? Okay. What is 1980 divided by 2? Is 990 divided by 2 divisible by 2?
Yes.
Yeah, it is. Okay, 2 times what?
491.
Is 495 divisible by 2?
No.
No. Is 495 divisible by 3?
Probably.
No.
Yes.
No.
18,
What is? Oh wait.
Carter says it is, guys.
Do you know how you check?
You
yeah.
add the digits.
You add the digits. So 4 plus 9 plus 5 is 18. 1 plus 8 is 9, and 9 is divisible by 3. So this is divisible by 3. And what's 495 divided by 3?
65?
Yeah.
Carter? I think so. Okay.
165. Okay, is 165 divisible by 3?
Yeah.
What is 165 divided by 3? 55. Is 55 divisible by 3? No. Is it divisible by 5?
Yes.
5 times 11. Okay, so now we go back, and every time we find a prime number, take note of it. We write 3,960. 3,960 is going to be equal to 2 raised to the power 3 times 3 raised to the power 2 times 5 times 11. This is called a prime factorization. Prime factorization is when you take any number and you break it down into its constituent primes, and you write them in general in order from least to greatest, and you list all of their multiplicities as little exponents. And that's it. Today we're just going to state this. We may or may not prove this in the future. It depends on how much time we have in this class. We'll find out. But this is called the fundamental theorem of arithmetic. It states, every integer greater than 1 is either prime or can be represented uniquely as an ordered product of prime numbers. That is the prime factorization. It means the prime factorization is unique. Every positive integer has exactly one prime factorization. You can't say that two numbers share the same prime factorization. And you can't say that one number has two different prime factorizations. It's a one-to-one correspondence. It's something a lot of us just take for granted. And for today, we're going to take it for granted. We're not going to prove it today. Maybe in the future, but
How do you prove that? That's just kind of true.
I know you are kind of getting to the point with math, sometimes where you're like, isn't that kind of obviously true? Like, do you really have to prove it? I mean, there is. Like, if you got free time, get on Wikipedia, search fundamental theorem of arithmetic, and Wikipedia will tell you how to prove it if you want to.
Somebody proved that.
Yeah.
How long did it take them?
I mean, the proofs are actually not that difficult to follow because it is very basic logic. But you're right. I mean, hopefully certain things are obvious enough you're willing to accept them, like in this case, the fundamental theorem of arithmetic. So here's a new problem for us to sit and mull over for a moment. We are given n disjoint sets, A subscript k, and a little bit of shorthand for the cardinality, or how many elements are going to be in these sets. We're going to say like the set A1 has lowercase a1 number of elements, right? Explain why the number of subsets of, what is this, the union of all of those sets AK. Explain why the number of subsets of this union that contain at most, not at least, that contain at most one element from each AK is this. To be honest with you, when I read a combinatorics problem, like this. Sometimes I have to read it twice or 3 times to really make sure I fully understand what the question is asking, you know?
That's not just you.
So I have sets A1, A2, A3, A4, and so on, up to AN, whatever that is. And they're disjoint, so they don't have any elements in common. And if I were to take the union of all of these, that gives me a new set. We could just call that capital A for the union of all of those sets. Suppose, for example, n is equal to 4, then this would be the case. And so when this is talking about subsets over here, explain why the number of subsets. Let's call this B. And so this subset B is going to be a subset of A, where A is the union of all of these A1, A2, A3, A4 subsets. And B contains at most one element from A1, and it contains at most one element from A2, and it contains at most one element from A3, and it contains at most one element from A4. In other words, B contains either 0 or 1 element from each of those, right? That's what at most means. So I'm interested in the question, the number of subsets. In other words, how many possible subsets B exist? And this actually gives us the answer to the question. The answer to the question would be the size of A1 plus 1 times the size of A2 plus 1 times the size of A3 plus 1 times the size of A4 plus 1. That's the answer to the question. But really, you know, as you're taking your test and you get this as a test question, you would have to explain why. Explain why this is true.
I'm trying to figure it out. I think I get it.
So like from the first A1 set, B either contains one element, which would be the plus one is basically is how you include the 0.
Yeah.
Or because it's either 0, which is where you add 1, or one element, which is the size of little a1. And then if you're looking for each combination, you would multiply them all together.
Yep. So that's great. If you had to choose one element from A1 and A2 and A3 and A4, then the number of possibilities would be like the size of each set multiplied together, A1 times A2 times A3 times A4. But in addition to just choosing one element from each set, you also have the option of just not choosing an element from the set, which is in a way kind of like adding another element to the set. That's where the plus one comes from. So I feel like you wrapped your mind around this. And sometimes even after I've figured it out and I feel like I understand what's happening, putting it into words is tough. Putting this into words is a little bit difficult. If you have to explain why as a test question, what would you write down? You would say, if B contained exactly one element from A1, A2, A3, and so on, then the number of possible B would be A1 times A2 times A3 times ... And this is because of the Cartesian product, right? Oops. In other words, the set B is an ordered tuplet where I'm selecting the elements from disjoint sets. But in our case, since B also has the option of not selecting an element from each set, this has the same result as adding another independent choice to each AK. Hence, plus one. Okay, so if I were taking a test, right, and I had, to answer one of these explain why questions, I feel like that explanation would get full credit because what you're trying to do is you're trying to demonstrate to me, the grader, that you know what you're talking about, that you fully understand the problem. Okay, let's move on to another one. Let the function lowercase d of x represent the number of divisors of the positive integer x, so that, what's the number of divisors of 10? There are 4 divisors of 10. What are they? 1, 2, 5, 10. Okay, we say that d of 11 is 2 because what are the divisors of 11? 1, 11. We say the number of divisors of 12 is 6 because what are those?
1, 2, 3, 4, 6, 12.
Good. Okay. Prove that if x has the prime factorization p1 to the m1 times p2 to the m2 times p3 to the m3, right? The way we did prime factorization a moment ago. Then this is true. And we were talking about this product symbol earlier. And so this is a product of a bunch of factors where each factor looks like one of those multiplicities plus 1. So this would look like the product m1 plus 1 times m2 plus 1 times dot 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 dot, right? However many of those factors exist, because we've got n different prime factors. So the question is asking us to prove that if we got a prime factorization, then this function that tells me the number of divisors is going to be the product of these multiplicities plus 1. What do you think? So I would start off my explanation by saying a divisor of x is a number that has to have the same exact primes in the prime factorization. P1, P2, P3, and so on. But for a divisor, it doesn't have to have the same exponents on the primes in the prime factorization. So I don't know what I should use for the exponent. I need a new symbol up here. Not m. Maybe if I didn't already use n here, I could use an n. There we go. So we'll call this n1, n2, n3. And the only rule about this number n is that it should be between 0 and m. Does that make sense? A divisor can't have any prime factors that the number x doesn't have. But it's okay if it doesn't have one of the prime factors. And it's okay if it has one of the prime factors raised to a smaller power. Okay, just like if I looked at 2 is the divisor of 10, 2 has 2 as a factor, just like 10 has 2 as a factor, but 2 doesn't have 5 as a factor. Okay, so that's the idea, is a divisor is going to be a number such that these powers of the primes are going to be somewhere between 0 and whatever the power of the prime is in the prime factorization of x. Does that help you? Does that get your brain juices flowing a little bit? So to write a divisor for each number k we choose from mk plus 1 possibilities. What are those mk plus 1 possibilities? That's 0, 1, 2, 3, 4, 5, up to mk. That makes a total of mk plus 1 possibilities. And so the product comes around because I'm making individual decisions that are independent from one another. I multiply the number of choices in each independent decision. Which corresponds to each p, k, and k. So now, if you can calculate the prime factorization of a number, you can count the number of divisors it has. Let's try using this. This is my prime factorization of the number 3,960. So how many divisors does the number 3,960 have? More than 4.
Wait. Oh.
38.
Okay, so the theorem we were just talking about said I need to take each one of the powers on the prime factors and add 1, like 3 plus 1, and multiply them, times 2 plus 1. 5 is raised to the 1 power, so that would be 1 plus 1. And then 11 is 11 raised to the 1 power, so that would be 1 plus 1. So in total, I get 4 times 3 times 2 times 2, which is what? 48. Very nice. The number 3,960 has 48 divisors. And if I want to construct one of these divisors, I just have to choose the same primes, 2, 3, 5, and 11. And for the number on 2, this could be anywhere between 0, 1, 2, or 3. Choose a number.
1.
How about 1? Yeah. And for 3, this could either be 0, 1, or 2. There's 3 possibilities, right? 0, 1, or 2. Let's call it 0. And for 5, this could be 0 or 1. Let's call it 0. And then for 11, this could be either 0 or 1, right? So let's call it 1. And this makes a divisor. And so 22 is a divisor of 3,960. But this didn't have to be a 1. This could have come from the set 0, 1, 2, 3. This didn't have to be a 0. It just had to come from the set 0, 1, or 2. This didn't have to be a 0. It just had to be a 0 or a 1. And this didn't have to be a 0. Or it didn't have to be a 1. It just had to be a 0 or a 1. In other words, you're limited by the power of the prime and the prime factorization, but you can be as low as 0 if you want to. And that's why the number of divisors is 4 times 3 times 2 times 2, because you're making a decision on each step. It's like if you have 4 choices of appetizer and 3 choices of entree and 2 choices of dessert and 2 choices of slushy. I don't know. So that's what we've been talking about. A perfect square is a positive integer that can be expressed as the square of another positive integer. So if y is a positive integer, y squared is equal to x. X is a perfect square. Explain why x is a perfect square if and only if the number of divisors is odd. Explain why x is a perfect square if and only if the number of divisors is odd. It might help if we write down the formula for the divisor function we got in the last exercise. And it also might help if we write down something that looks like a prime factorization for x. And it also might help give you guys a little hint. If we write down a prime factorization for y, if x is a perfect square, it has to be equal to some other positive integer squared, right? And so y would have a prime factorization of some primes. I'll give you a few minutes to think about this. Who can explain that to me? Connie?
Is it because like the number of factorizations is usually even, but since it's a square, like 7 will show up twice and 49, and so.
Yeah. You're on the right track.
Okay, I started this off, guys. You guys got this.
It's a great start. Do these prime factors for y have to be the same prime factors as x? Yes. The prime factors of x must be the same prime factors of y. And if we call these multiplicities on the y prime factorization n's, call that n1, n2, n3, n4. What is the relationship between m1 and n1? How is m1 related to n1?
N1 equals 2n1.
Nice. And for that matter, how is m2 related to n2? Yeah, for every single prime factor, the multiplicity you get in the x prime factorization is twice the multiplicity you get in the y factorization. So for all of the multiplicities in the x factorization, what can I say about them?
They're all even.
They have to be even. If I multiply a number times 2, it has to be even. All of these multiplicities are even. Okay. Now go back to my formula here for the divisor function. D of x is equal to the product of factors that look like mk plus 1. If mk is even, what's mk plus 1? Odd. If I multiply a bunch of odd numbers together, I get an odd number, right? 3 times 5 times 7 times 9. Product of a bunch of odd numbers is always odd. And so that would give me an odd divisor. In the reverse direction, right, like if I'm trying to prove this if and only if statement, I have to not only show that if x is a perfect square, that implies that this divisor is odd. We just discussed that together. But I also have to explain why getting an odd number of divisors would have to imply that x is a perfect square. And so think about this. Conversely, if this is an odd number, there cannot be any even factors. Because if there was an even number in this product, an even factor would immediately make this even. So that means none of these are even numbers. They're all odd numbers. So now let me subtract 1 away from an odd number, and it necessarily gives me an even number. And that means mk is an even number. And if all of these mk's are even numbers, that means I could divide an even number by 2 and get a whole number, a whole positive integer number, and that means I could construct a number y with this prime factorization so that y squared equals x. So you'd have to write something down on your paper that follows that verbal explanation I just gave you in order to get points on a test. But it's 3 o'clock, so y'all have a great day.